In a certain region with hawks as predators and rodents as prey, the rodent population R varies according to this model, and the hawk population H varies according to this model, with T measured in years since January 1st, 2010. Okay, so we're going to have population of hawks, population of rodents, and we're going to have the hawks eating the rodents and the rodents running for their lives. How many hawks were there on January the 1st, 2010? We're using the hawks formula, so we're going to use this one, not the first one they gave us. So we're going to plug in a number into that. I wonder what we're going to plug in. Okay, well, January 1st, 2010, how many years has it been since January 1st, 2010 on January 1st, 2010? Well, 0 time has passed. We're going to plug in a 0 into the hawk formula, and we're going to have 250 plus 25 pi over 2, t minus 1/2. And we're going to figure this out. Oops, instead of t, I'm going to plug a 0. Sorry about that. Now, I can get really technical here, and we can try to figure out exactly what this is using all kinds of fantastic stuff, or you could graph it, okay? Totally feel free to graph it. And you have a graph at the bottom of your paper that will help you sort of understand this. And in order to do that, in order to really explain it, I have graphed it on Desmos, and I have printed that. So I have this graph. You don't have to draw it, but if you did, you'd get that, right? You got that? Good. Okay, so this is the number of rodents, and this is the number of hawks. And we could look at this, look at these two graphs and really tell a lot. And we're going to in a minute. But in the meantime, let's finish answering the question. How many hawks were there on January the 1st, 2010? That would actually be at 0. So it'd be this dot right here. And I don't know where that is. And on Desmos, you can click it and find it. But I want to point out something that's about to happen here. Usually, and I'm going to look at this formula, usually I'd say, oh man, look at that vertical shift. That's my starting point. Yeah, I hear you. You're right. You're good. You're fine. For rodents, not for hawks. And here's why. There's a horizontal shift that happens in this one, and we haven't dealt with a horizontal shift. But what normally would have a vertical shift of 250, and it does, is also going to have a horizontal shift that's going to tilt things, not tilt. Tilt's the very wrong word. It's going to shift things, literally, left or right. Right, 1/2 actually. And when you do that, you're not going to have necessarily a y-intercept of 250, okay? Just throwing that out there. So I'm going to continue to do this as much as I can by hand. 250 plus 25 sine, my goodness, what a mess. I left that sine off. 25 sine of, let's see, pi over 2 times 0 minus 1/2. So that's going to be negative pi over 4. And sine of negative pi over 4, man, we're pulling out some unit circle, aren't we? 250 plus 25. Let's see, sine of negative pi over 4 is the negative square root of, no, positive square root of 2 over 2. So square root of 2, no, negative square root of 2 over 2. There we go. At this point, I am going to grab a calculator, and we're going to finish this, and we'll get 250 plus 25 times negative square root of 2 over 2. And we have 232, let's round to the nearest hawks. Now, I wanted to go through that just to demonstrate, first of all, that I had left the word sine off there, and that's tragic. Please fix it. I also wanted to demonstrate that you can find this somewhat by hand up to a point, but when you do, it's going to correspond to that point right there. I've printed 2 versions of this, one with those dots. So 232. Now, we already know the other one. It's going to be 1,200. So we can go ahead and answer the next question. How many rodents were there? So 0. And plug in a 0 for that. And you're going to get, well, 1,200. So it's 1,200 plus 300 sine of pi over 2 times 0. Pi over 2 times 0 is 0. So I'm telling you, we're about to get a 1,200 here, but I just want to show it to you. 300 sine of 0. Sine of 0 is 0, so we're left with 1,200 plus 0, which is 1,200 rodents. Okay, find the maximum and minimum numbers of hawks and rodents. Let's just stop and do that before we read forward and get all confused and stuff. So we're going to have hawks maximum, hawks minimum. We're going to have rodents maximum and rodents minimum. Let's just organize it in a table like this. Okay, cool. Do these extrema ever occur at the same time? Why or why not? Well, we can look at our graph and figure this out, but let's actually look at these and figure it out. So if my midline is 1,200 for rodents, and I can go up 300, then I can have as many as 1,500. Or I can go 1,200 minus 300 and get 900, right? Okay. My midline is 250. That is not my y-intercept, but it is my midline. The middle of this graph is 250. 250 plus 25 is going to give me 275. And 250 minus 25 is going to give me 225. So I have answered the questions in the first sentence, done what they told me to do. But do these extrema ever occur at the same time? No. No, they don't. Because there's a shift in the graph. And again, it's this horizontal shift that we haven't discussed, but notice it's a 1/2 shift, which actually would take what would be a maximum and shifted it over half. You see it? So there should be a maximum here, but that minus 1/2 shifted this over. Okay, so do these extrema ever occur at the same time? No, these extrema, these extreme values, is Latin, do not occur at the same time. Okay, I am not going to give, well, I am. Because, I was about to say I'm not going to give a mathematical reason, I'm going to give a biological reason. I'm going to give both. Because h of t has a horizontal shift, and r of t does not. Okay, that's the mathematical reason. Here is the biological reason. This is really neat. Look at the graphs. We have a whole lot of rodents up here. Rodents. Did this on the other graph, but now we have numbers on this one, and this is going to be hawks. I have a whole lot of rodents. When I have a whole lot of rodents, then the hawks have a whole lot to eat. So they start eating, and they eat more. Their population increases because they have an abundance of resources. The rodent population goes down. It goes down to a point where once we get here, the hawk population is beginning to decline as well because they aren't going to have as many rodents to feed on. They have less resources because they have, don't worry, we're not going to write all this down, but they have less resources, so they begin dying out some more. As the hawks continue to die out, the number of rodents, they don't have more people, they don't have as many predators, so the rodent population increases. So they're not going to be going at the exact same, like you're not going to have hawks and rodents. That's not going to happen. They won't peak at the same time because an abundance of food is going to cause them to eat more, which decreases the amount of food they have, which causes this population to go down, which means there's less people, less hawks eating the rodents, people eating rodents, less hawks eating rodents, so then they can increase in population. So I said it, I didn't write it, I have given the mathematical reason, but the biological reason is hidden in the graph and in just plain common sense that you can't have parallel sinusoidal graphs when you're dealing with predator and prey.